Good day everyone and welcome to our first lesson. Today we will be discussing about composition stoichiometry. Let's start with a definition of the term stoichiometry. So stoichiometry was coined from the Greek words stoichion, meaning elements, and metron, which means to measure. And then they put the two terms together and then they came up with stoichiometry. As a brief definition, stoichiometry defines the mass to mole relationships in a chemical reaction, leading to a quantitative analysis of any chemical reaction. In other words, stoichiometry deals with the conversion from one quantity to the other in a chemical reaction. Here are the list of the related concepts that we will be discussing in our study of stoichiometry: atomic mass, mole, Avogadro's number, chemical formula, percent compositions, and chemical equations. So these topics should just be a review for you. So let's refresh your memory. Let's first start with atomic mass. So atomic masses represent the average of the atomic masses of all known naturally occurring isotopes of an element. So basically, the atomic mass that you are reading from a periodic table, that is the average atomic mass of all of the known naturally occurring isotopes of the elements. So for example, in hydrogen, there are three known isotopes. So they are the same element, but they are just varying in their number of neutrons. So we have the proton, that's H1, we have deuterium, H2, and we have tritium, H3. The listed atomic mass of hydrogen in the periodic table is the average of the atomic masses of all of these three naturally occurring isotopes. For atomic mass, we are using the unified atomic mass units, signified by the letter U, or Daltons. But you are more familiar with the units of grams per mole in the atomic mass. So we're going to use grams per mole as well. Technically, atomic mass is defined as 1/12 the mass of a single atom of carbon 12. I have previously mentioned that the atomic mass listed in the periodic table of elements is the average of the atomic masses of the naturally occurring isotopes of that element. And that's what we call relative abundance. The abundance of the naturally occurring isotopes of a given element are the basis for the average atomic mass. And it's very easy to compute. It's as simple as taking the weighted average of the atomic masses of the individual isotopes. So let's try it with this example. Chlorine has two naturally occurring isotopes. That's chlorine 35 with atomic mass of 34.9689 U and chlorine 37 with the atomic mass of 36.9659 U with relative abundance of 75.76% and 24.24% respectively. What is the average atomic mass of chlorine? Let's try to solve this example. So I have listed here our given. So again, for chlorine, we have the two naturally occurring isotopes, chlorine 35 and chlorine 37 with their atomic masses listed there, as well as their percent abundance. So how do we compute the average atomic mass of chlorine? That is simply done by multiplying the percent abundance to the corresponding atomic mass of the isotope. So we write it as 75.76%. So we are simply converting it to a decimal notation multiplied by 34.9689 atomic mass units. This is for chlorine 35 plus 0.2424 or 24.24% multiplied by the atomic mass of chlorine 37, 36.9659 atomic mass units. And you simply enter that in your calculator, then we will have the average atomic mass of chlorine. So that is 0.7576 times 34.989689 plus 0.2424 times 36.9659. That is 35.45 atomic mass units. That is the average molecular weight of chlorine. So if you take a look at a periodic table, this is the atomic mass for chlorine that you will see because that's already the averaged atomic mass for all of the naturally occurring isotopes of chlorine. Okay, so you can do this with all of the other elements. Let's proceed. We have here another problem. Silicon has three naturally occurring isotopes with atomic masses and relative abundance listed on the table below. What is the average atomic mass of silicon? Now that you know that you will just be getting the weighted average of the atomic masses, we can even do it without writing the formula. You simply multiply the percent abundance to the atomic mass and then you simply add all of those products. You can try that with your calculator. Next. Now let's define the mole because the concept of the mole along with its conversion with mass is very important in chemistry. A unit of measurement defined as an amount of substance with the same number of particles as there are in 0.012 kilograms of carbon-12. That is a very technical definition of the mole, and we will circle back to the concept of the mole later. Let's first define Avogadro's number. So Avogadro's number is a physical constant with a value of 6.022 times 10 raised to 23. Now, what is the significance of this Avogadro's number? This is tied to the concept of the mole because 1 mole of something means that you have Avogadro's number amounts of particles. So let's say, for example, if you have 1 mole of eggs, that means that you have 6.022 times 10 raised to 23 pieces of eggs. And that's a very, very big number. That is 6022 followed by 20 zeros. Okay? We use the concept of Avogadro's number in conjunction with the definition of the mole to define how many atoms of a substance are there in a given mole of the substance. So another example here, if you have 1 mole of sodium, that means that you have 6.022 times 10 raised to 23 atoms of sodium. So do not forget about this conversion. The conversion from mole to the number of particles. So when we say particles here, we can be referring to atoms. We can also be referring to molecules. And we can also be referring to other types of particles. Okay? Next, let's define molecular weight. So molecular weight is a very important conversion factor in chemistry because molecular weight gives you the avenue in converting from mass to moles or vice versa. The definition of the molecular weight is the amount of mass of a substance divided by its number of moles. Okay? And this is where the unit grams per mole is derived based from the definition of molecular weight. The mass translates to grams, and then the mole translates to mole as the unit. Okay? The unit Dalton is equivalent to the unit grams per mole. So now that we have defined mole, Avogadro's number, and molecular weights, we can now define the relationships between mass, mole, and number of atoms. We will now be drafting a chart that relates mass to mole to number of atoms so that you will not forget. We have 3 quantities, that is mass, mole, and the number of atoms. If we want to convert from mass to mole or mole to mass, we are going to use the molecular weight as our conversion factor. The molecular weight can be obtained from the periodic table of the elements. When we want to convert from moles to number of atoms or vice versa, we are going to use Avogadro's number, 6.022 times 10 raised to 23. Now, there is no direct conversion from mass to number of atoms. If you want to convert from mass to number of atoms, what we need to do is to first convert mass to mole and then convert mole to number of atoms. So it's a 2-step process. Okay? So do not forget this chart. Let's try some examples. Okay, first one. How much does 3.5 moles of aluminum weigh? So let's try to solve that. You are given 3.5 moles of aluminum and we are asked how much does it weigh. So that implies that we want to convert the moles of aluminum to grams of aluminum. And how do we do that? If you go back to our chart earlier, if you want to convert from moles to mass, we must use the molecular weight of the substance. And our substance in this case is aluminum. So let's look for the molecular weight of aluminum. I have here a periodic table of the elements. And you see here, aluminum has a molecular weight of 26.982 grams per mole. So let's write that. The molecular weight of aluminum is 26.982 grams per mole. Now, this molecular weight is an important conversion factor for us to convert from moles to mass. Let's use the unit factor analysis method for our conversion. We start with the given, that's 3.50 moles of aluminum. And since your unit here is moles, that means in our next factor, moles should be in the denominator. And that makes grams our unit in the numerator. So that means that we will multiply the molecular weight to the number of moles to obtain the mass. We get 3.5 times 26.982. 94.437 grams of aluminum. Now, the given is three significant figures, so we must only retain three significant figures in the answer. That's 94.4 grams aluminum. So that is how we use the molecular weight in converting from mass to mole. Okay? Next. Okay, next problem. How many moles are there in 200 grams of osmium? So the given is 200 grams osmium. We want to know the number of moles. So let's try to solve this. We are converting from grams to mole. So we still need the molecular weight as our conversion factor. So let's look for the molecular weight of osmium. So from our periodic table, osmium is 190.23 grams per mole. 190.23 grams per mole. And then we use the same unit factor analysis method. We start with the given, 200 grams of osmium. And this time, grams is our unit, so we need to have grams in the denominator of the factor for it to cancel. So grams below, moles at the top. That means that we are dividing by the molecular weight of osmium. 190.23 grams is to 1 mole of osmium. So grams of osmium cancels. We are left with the unit moles of osmium. We can now compute for the number of moles of osmium. That is 200 divided by 190.23. And assuming that the two zeros in 200 are significant, we retain three significant figures. That is 1.05 moles of osmium. Next problem. How many atoms are there in 1 gram of carbon? So based on this given, we are now converting from mass to number of atoms. If you consult our chart earlier, there is no direct conversion from mass to number of atoms. So we need to convert first from mass to mole and then from mole to number of atoms. So let's write the given. We have 1 gram of carbon and we want to know how many atoms are there in this sample. Okay, so our plan is again, from mass, we first convert this to mole using the molecular weight because the molecular weight is the conversion factor from mass to mole. And then from mole to the number of atoms, we use Avogadro's number as our conversion factor. Okay, we start with a given 1 gram of carbon. First unit refers to the molecular weight. And if we go back to our periodic table, the molecular weight of carbon is 12.011 grams per mole. And since grams is our unit for the given, that means that grams should be in the denominator and mole is in the numerator. So we are dividing with the molecular weight. 12.011 grams of carbon is to 1 mole. Gram of carbon cancels. Next factor, we want to convert from mole to the number of atoms. So we are using the Avogadro's number as our conversion factor. Avogadro's number states that there are 6.022 times 10 raised to 23 atoms for every mole of the substance. So we can use this relationship in our last factor. So in our previous factor, mole is in the numerator. That means in the next factor, it should be in the denominator, moles carbon. And our numerator is atoms of carbon. And using the value of Avogadro's number, we write 6.022 times 10 raised to 23 atoms of carbon per 1 mole of carbon. The number of moles of carbon cancels, and we can now compute for the number of atoms. We compute as 1 divided by 12.011 times 6.022 times 10 raised to 23. Answer, in 3 significant figures, 5.01 times 10 raised to 22 atoms of carbon. Okay, so this is how we convert from mass to number of atoms. If you're given number of atoms and you want to convert it to mass, you simply follow the same path but in reverse. Okay? Last problem, how much does a single oxygen atom weigh? So I will be leaving this problem to you as an exercise so that you can practice. In this one, we are converting from atoms. So you have one atom, you want to convert it to mass. Okay, so it's just the reverse of our previous example. Let's proceed. The next concept that we will be discussing is chemical formula. Chemical formula are very important in the study of chemistry because these are used to represent elements and compounds in an equation. And chemistry is all about chemical reactions. No? So you need to learn about chemical formulas. Chemical formula are governed by the law of definite proportions. Just to refresh you, the law of definite proportions states that for every compound, there exists a fixed ratio between its constituent atoms. And if you were to change that ratio, you will end up with a different compound. Okay? So that's the law of definite proportions. The molecular weight of a compound is simply the sum of the atomic masses of each atom in a compound. So you will just be adding atomic masses. For example, determine the molecular weight of water. Water has a chemical formula of H2O. That means that it has 2 atoms of hydrogen and 1 atom of oxygen. So if you want to determine the molecular weight of water, we need to know the atomic masses of hydrogen and oxygen. So let's try to solve that. Your given is H2O. Again, you have 2 atoms of hydrogen and 1 atom of oxygen. Let's look at the periodic table for the molecular weights. For oxygen, the molecular weight is 15.999 grams per mole. And for hydrogen, the molecular weight is here 1.008 grams per mole. Okay, so there's our given. Now, we need to multiply that molecular weight with the number of atoms present in the compound. So for oxygen, there's only 1. So we need to multiply 15.999 by 1. And for hydrogen, there's 2. So we need to multiply 1.008 by 2. So we have 15.999 for oxygen. And for hydrogen, we have 2.016. Next, it's just a matter of adding these two to get the molecular weight of water. The molecular weight of water is simply 15.999 plus 2.016. That is 18.015 grams per mole. So we have determined the molecular weight of water. Okay, so that is how you compute for the molecular weight of a compound. You must know its chemical formula because without the chemical formula, we cannot know the number of atoms in the compound. Okay, let's try the next one. Determine the molecular weight of sucrose. So sucrose is table sugar. This is the sugar that you add to your coffee and to your other drinks. Its chemical formula is C12H22O11. Let's determine its molecular formula. We will just be repeating our process from earlier. No? So we list the atomic masses of the individual elements. We multiply them by the number of atoms in the compound and then add. So let's start with oxygen. That is 15.999 multiplied by 11. For hydrogen, that is 1.008 multiplied by 22. And for carbon, that is 12.011 multiplied by 12. And we simply multiply. First, for oxygen, 15.999 times 11, 175.989. Next, for hydrogen, that is 22.176. And lastly, for carbon, (144.132). And then get the sum, we get the molecular weight of sucrose. That's 144.132 plus 22.176 plus 175.989. That's 342.297 grams per mole. So that is how we compute for molecular weights of compounds. Okay? So if you are performing stoichiometry using compounds, this is how you determine its molecular weight. Let's proceed. Next is percent composition. This tells us the elemental composition of a compound in terms of percentage by weight. In order for you to determine the percent composition, you must first determine its molecular weight because the molecular weight factors in the calculation of the percent composition. Let's try this example. Determine the percent composition of the elements in aluminum sulfate. Okay, the first question is, what is the chemical formula of aluminum sulfate? You noticed that aluminum sulfate there was given as a proper name and it was not given as a formula. So it's up to us to determine the molecular formula of aluminum sulfate. Based from your previous learnings, aluminum as a cation has a charge of +3, and sulfate is an anion with the formula of SO4 with a charge of 2-. So if we're going to apply the crisscross method, we drop the signs and then the 3 goes for the sulfate and then the 2 goes to the aluminum. Our formula becomes Al2 and then SO4 3. This is the chemical formula of aluminum sulfate. Now we can determine the percent composition of the elements. We have three elements here: aluminum, sulfur, and oxygen. The process of obtaining the percent composition starts with determining the molecular weight of the compound. So let's first determine its molecular weight. For oxygen, that's 15.999 multiplied by 12. So this is 4 times 3. Okay? Remember that the subscript 3 applies to the entire sulfate anion. You will need to multiply 3 to both the sulfur and the oxygen. Next is sulfur. Let's look for the molecular weight of sulfur. So sulfur is 32.06. Multiply that with 3. And then lastly, we have aluminum. Aluminum is 26.982 times 2. And then we multiply. So that is 15.999 times 12. That's 191.988. Next, for sulfur, 32.06 times 3, 96.18. Next, for aluminum, 26.982 multiplied by 2. That's 53.964. And then we add to determine the molecular weight of aluminum sulfate. So that's 53.964 plus 96.18 plus 191.988. So the molecular weight is 342.132 grams per mole. Now we will be solving for the percent composition. For the percent composition, we are just going to divide the molecular weight per element to the molecular weight of the entire compound. So let's say, for example, for oxygen, we just need to compute the percent composition as 191.988. This is the total atomic mass of oxygen in aluminum sulfate divided by the total molecular weight of aluminum sulfate, 342.132. And that is times 100 to make it percent. So our answer is 56.12%. Okay? We do the same for sulfur. So the total atomic mass of sulfur is 96.18. You divide that with the molecular weight 342.132 times 100 to make it percent. That's 28.11%. And then lastly, for aluminum, the total molecular weight is 53.964. Divide that 53.964. Divide that with 342.132 times 100. We get 15.77%. And if you did everything correctly, if you total the percent composition of the individual elements, you should arrive with 100% to know that you are correct. So let's check. We have 56.12 plus 28.11 plus 15.77. The total is 100%. We know that we performed the correct computations. Now, if you obtain 99.99 as the total or 100.01%, that's okay because that might be due to rounding off error. Okay? So that is how we compute for the percent composition of the compound. We have here a do-it-yourself. You simply follow the same solution, but this time you are to determine the percent composition of the elements in calcium phosphate. You also have three elements: calcium, phosphorus, and oxygen. you follow our example earlier and you can find the percent composition of calcium phosphate. Okay? Do this as your practice. Next. Next, we have empirical and molecular formula. So these are two related topics. These are two related topics that are connected with the percent composition. Since the elements in a compound exist at a fixed proportion, which is dictated by the law of definite proportions, you can use percentage composition data to determine the empirical formula. In our previous slide, you are given the chemical formula and you are to solve for the percent composition. This time around, you will be given the percent composition and we will manipulate those numbers for us to determine the chemical formula. And chemical formulas come in two types, the empirical and the molecular. So what's the difference? The empirical formula is the simplest positive integer ratio of atoms present in a compound, and it's not the same as a molecular formula. So the empirical formula is a simpler version of the molecular formula. The molecular formula lists the complete atomic composition of a compound. For you to be able to differentiate between empirical and molecular formula, here are some examples. And by the way, please do take note that empirical and molecular formulas can sometimes be the same, not all of the time. Okay? First example, you can have an empirical formula of NO2, but also have a molecular formula of N2O4. If you notice, we simply multiplied NO2 by 2. So that became N2 and then O became 4. Another example, you can have an empirical formula of CO2 and a molecular formula of C2O4. Again, we multiplied this by 2. And then last example, you can have an empirical formula of H2O and also a molecular formula of H2O. So this is a case wherein the empirical and molecular formula are the same. Let's try to solve some problems regarding empirical and molecular formula. A compound contains 21.6% sodium, 33.3% chlorine, and 45.1% oxygen. Determine the empirical formula of the compound. So notice that your given here is the percentage composition, which we have determined earlier. But this time, we don't know the chemical formula of the compound. We need to determine the empirical formula. Let's solve for that. Our given is we have 21.6% sodium, 33.3% chlorine, and 45.1% oxygen. Okay. Now for these types of problems, remember that this composition is in terms of mass, or this is percent by mass. For our first step in the solution, we are going to assume that we have 100 grams of the compound. So you might be asking, why did I choose to assume that I have 100 grams of the compound? This is for simplicity reason. If you multiply 100 by 21.6%, the answer is 21.6 grams. So it's not complicated to determine the mass of the elements if you assume that you have 100 grams of the compound. So in theory, you can assume any type of number in your initial assumptions. Let's say, for example, you want to assume that there's 42.67 grams of your compound. That's okay, but you would be adding another layer of calculations because you need to multiply 42.67 with 21.6%. In easy terms, by assuming 100 grams of the compound, that means that we have 21.6 grams of sodium, we have 33.3 grams of chlorine, and we also have 45.1 grams of oxygen. Okay, that's the beauty of assuming 100 grams. Now we have to convert this to moles. No? We have 3 atoms, so we need 3 molecular weights for sodium, for chlorine, and for oxygen. Let's convert first for sodium. Let's take a look at the molecular weight of sodium. That is 22.99. So we divide by the molecular weight to convert it to mole. The molecular weight of chlorine is 35.45 grams is to 1 mole. And the molecular weight of oxygen is 15.999 grams per mole. Let's compute for these numbers. For sodium, 21.6 divided by 22.99. You can use 4 decimal places. So that's 0.9395. For chlorine, that's 33.3 divided by 35.45. We get 0.9394. And for oxygen, 45.1 divided by 15.999, we get 2.8189. So these are all in moles. Moles sodium, moles chlorine, and moles oxygen. Now, what's the next step? We now have the number of moles of each of your elements. We need to divide them by the lowest value that you obtained. Out of the 3 moles that we obtained, the lowest is 0.9394. You divide everything by 0.9394. Now we can get the number of atoms in the compound. So for the first one, 0.9395 over 0.9394 is very, very close to 1. So we will label that as 1. For chlorine, it's also 1. Now for oxygen, that's 0.2189 divided by 0.9394. And we get a value of 3. So for these types of computation, it's okay to round it up to the nearest whole number. Okay? So these numbers that we have obtained, these are already the count of the atoms in the compound. So that means that the empirical formula of the compound is now Na1 Cl1 O3. This is our empirical formula. Okay? The determination of empirical formula for any compound follows the same procedure as long as you are given the percentage composition. So again, from the percentage composition, you assume that you have 100 grams of the compound so that you can get the masses. You convert the masses to moles, and then you divide all of the moles with the lowest value that you obtain. And that gives you the count of the atoms for the empirical formula. Let's try the next example. Vitamin C, or ascorbic acid, was found to contain 40.91% carbon, 4.59% hydrogen, and 54.50% oxygen. Determine its empirical formula. So we are going to follow the same procedure. Okay, the given 40.91% oxygen, 4.59% hydrogen, and 54.5% oxygen. Okay, so next, we assume that you have 100 grams of the compound. And doing so, we obtain 40.91 grams of carbon, 4.59 grams of hydrogen, and 54.5 grams, 54.5 grams of oxygen. Now we can convert this to moles. So the molecular weight of carbon is 12.011. For hydrogen, that is 1.008. And for oxygen, that is 15.999. Let's compute. 40.91 divided by 12.011. we get 3.406 moles of carbon. Next, for hydrogen, 4.59 divided by 1.008, we get 4.553 moles of hydrogen. And lastly, for oxygen, 54.5 divided by 15.999. We get 3.406 moles of oxygen. Okay? After we have obtained the number of moles of the elements, we divide them by the lowest value that we obtained, and that is 3.406. Okay, so for carbon, that is 1. For oxygen, that is also 1. For hydrogen, that's 4.553 divided by 3.406. That's 1.337. In this case, 1.337 cannot be rounded down to 1, and it cannot be rounded up to 2. What we're going to do is we need to multiply all of those obtained numbers with an integer such that the result would also be an integer or a whole number. Okay? What can you multiply to 1.337 to make it a whole number or to make it very, very close to a whole number? Let's try 2. So if you multiply this by 2, you get 2.67. So that's not a whole number. So let's go back. If we multiply this by 3, we get 4.01. That is close enough to a whole number, which is 4. Now we know that we need to multiply 3. You multiply 3 to everything. So that is 1 times 3 and 1.337 times 3 and 1 times 3. So our results would be, this is 3, this is 4, and this is 3. Thus, our empirical formula for ascorbic acid is now C3H4O3. Okay, so let's proceed with the next item. From other experiments, it was shown that the molecular weight of ascorbic acid is 176.14 grams per mole. Determine its molecular formula. So this is a continuation of the previous item. Now that we have the empirical formula of ascorbic acid, the question is, how do we determine its molecular formula? I have listed the empirical formula of ascorbic acid from our previous calculations, and it was stated in the problem that the molecular weight of ascorbic acid is 176.14 grams per mole. Okay, for the determination of the molecular formula, we need to know two values. First is the molecular weight of the compound, and second is the empirical weight of the compound. The empirical weight is simply the molecular weight of the empirical formula of the compound. So the empirical formula, C3H4O3, we determine the empirical weight as oxygen, 15.999 times 3, plus hydrogen, 1.008 times 4, plus carbon, 12.011 times 3. And the empirical formula is 88.062 grams per mole. Now we are going to divide the molecular weight with the empirical weight in order for us to obtain an integer. So that is 176.14. This is the molecular weight. Divide that by the empirical weight, 88.062. What do we have? 176.14 divided by the empirical weight. Our integer is 2. So what do we do with this integer? You multiply this integer with the empirical formula to get the molecular formula. So therefore, the molecular formula of ascorbic acid is equal to 2 times the empirical formula of C3H4O3, we get a molecular formula of C6H8O6. Okay, so that is how we determine the molecular formula of a compound. That's the end of this lesson. For our next lesson, we will be dealing about reaction stoichiometry or performing stoichiometric calculations for chemical reactions, and that will be for next week. So if you have any questions with this lecture, you can always message me in course messages in Blackboard. Okay? That's it for this lesson. I hope you've learned something, and as always, keep safe.